Right, thank you everyone. Let's get going. So we started chapter 2 last time, which is about approximation of functions, and I got as far as writing a definition, which is what it meant for a series of functions to converge either pointwise or uniformly. And anytime you have uniform convergence, the domain can be critical in whether you have uniform convergence or not. So, for example, if we have the Taylor series e to the x, which is 1 plus x squared over 2 factorial plus and so on, then the series converges pointwise to the function e to the x on the whole real line, but it doesn't do so uniformly. And the reason for that is that if we look at the difference between two partial sums, for uniform convergence, they have to be uniformly small over the whole domain. But if I look at the n plus first partial sum minus the nth partial sum, this is just the m plus first term, which is x to the m plus 1 over n plus 1 factorial. For uniform convergence, that would have to be less than epsilon for n large enough, and for all x. But this goes to infinity as x goes to infinity. So if you want uniform convergence over the whole real line, you're out of luck, because the gap between two consecutive terms, however far out you go, the gap goes to infinity as x goes to infinity. So no uniform convergence on the whole real line. As we'll see shortly, such series will converge on compact intervals uniformly, but not on the whole real line. Okay, so the main way that you can determine uniform convergence of a series is something called the Weierstrass M-test. Generally speaking, uniform convergence could be quite a difficult thing to determine. And so we need a method, and this one works in most of the situations that one is interested in. So it says the following. Let sigma 1 to infinity fn of x be a series of bounded functions and the domain doesn't really matter. Any set S could be an interval, could be the whole real line, or maybe the functions are defined somewhere else. So the domain is essentially irrelevant in this case. Suppose there is a sequence m m sub n greater than or equal to 0 of constants so that the infinity norm of Fn is bounded by these constants and the sum from 1 to infinity of the constants converges. Now that's just a sequence of real numbers, or a series. Well, the conclusion is that I have no eraser. Well, that's the end of the class for today. I'll be back in a moment. I'm sure one of these rooms. Luckily, we seem to have this corner of the world to ourselves. Right, so then sigma Fn of x converges uniformly on the set S. And it's quite a simple thing. We have to show that the sequence of partial sums converges in the infinity norm. So we'll show that it's Cauchy in the infinity norm. So for m less than n, we have that the difference Sn minus Sm is the sum k equals m plus 1 up to n of fk of x. That's the difference between two partial sums of the series. So we have to estimate its infinity norm, and we'll do that with the triangle inequality. The infinity norm of Sn of x minus Sm of x is bounded by the sum k equals 1 to n, m plus 1 to n, of the infinity norms of the fk's. But the hypothesis is that the infinity norm is bounded by these constants. So this is less than or equal to the sum k equals m plus 1 to n of the m sub k's. Now that last term is simply the difference between the nth and the mth partial sum for the series sigma mk. Since that is convergent by hypothesis, since sigma mk converges, given epsilon greater than 0, there exists a capital N so that the absolute value epsilon for m and n greater than or equal to capital N. But that's exactly the estimate here. So therefore, the infinity norm of the nth partial sum of the series of functions minus the mth partial sum is less than epsilon for any m and n greater than or equal to capital N. And therefore, the sequence of partial sums converges uniformly. It's a uniformly convergent sequence, and therefore, by completeness of its continuous functions, therefore, the series converges uniformly. Okay, so that is the main way that we can decide uniform convergence. So if we return for a moment to that series for e to the x, from 0 to infinity x to the n over n factorial. Although we saw that it didn't converge uniformly on the whole real line, this converges uniformly on any interval minus a to a. And the reason is that if we look at individual terms, on that interval, how large can x to the n over n factorial be? Well, it can't be any bigger than a to the n over n factorial. So those are the capital M sub m's of the Weierstrass M-test. And this is a convergent series because sigma a to the n over n factorial from 0 to infinity is actually e to the a. So we have uniform convergence by the Weierstrass M-test. This is pretty typical behavior for series. They will generally not converge uniformly over the whole real line, even if they do converge pointwise, but on any compact interval, we will find that they do converge uniformly. Almost exactly for the reason that this one did. So let me just tell you where we're heading in the next lecture or two. We're going to try to prove the Weierstrass approximation theorem, which says that on any compact interval, any continuous function is uniformly approximable by polynomials. In order to do that, we're going to have some detailed knowledge about one or two series, and that's where we're heading now to get that. And also, since it's no more difficult, we'll look at the general theory of convergence of series because it can all be done with the Weierstrass M-test. So here's a theorem. Let Fn be a sequence of continuous functions on some interval AB, with continuous derivatives Fn prime of x. Suppose that the series sigma Fn prime of x converges uniformly on the interval AB and there is some point C in the interval AB at which the original series, when you plug in the value x equals c, this converges. So there we're talking about convergence of a sum of just numbers. Well, the conclusion is that the original series converges uniformly on the closed interval AB. And not only that, it is differentiable and its derivative is equal to the sum of the individual derivatives. And we refer to that by saying that the series is differentiable term by term. So if you think of just ordinary calculus, you never saw a theorem that said if you have an infinite sum, then the derivative of the sum is the sum of the derivatives. And in general, it won't be true. Differentiation does not pass through some infinite sums easily, but this is a setting where it does. So it's the best of all possible worlds. It's exactly what you would hope for. After we're done with the proof, I'll explain this rather mysterious condition that the original series should be summable at least one point. Because actually, if you take out that hypothesis, it's not true, for rather trivial reasons.
Is this also sufficient for the characterization to characterize when the derivative
changed it to the real line, then the theorem will still be true, but it definitely won't reverse. And the example for that would be, see, if you took the series sigma x to the n over n squared, because sigma 1 over n squared no, actually, forget that. I don't think that's a good example. Maybe one will occur to me. Okay, so let's do the proof. So we have uniform convergence of the derivatives, and they're all continuous functions. So let us define g of x to be the sum from 1 to infinity f prime of x dx. Just fn prime. Since the series converges uniformly, that means that the limit is continuous also. So that means that on the interval a to b, we can integrate. So let's write Sn of t for the nth partial sum of the derivatives. And because I'm about to integrate, I've changed the letter to t. Then because of the uniform convergence, given epsilon greater than 0, there exists a capital N so that the infinity norm of g of t minus Sn of t is less than epsilon over b minus a for n greater than or equal to capital N. And therefore, on the interval a to b, we have that g of t minus Sn of t is bounded above by epsilon over b minus a and bounded below by minus epsilon over b minus a. So now I'm going to integrate. So let's write capital G of x. Remember, we had this one point C where the original series converged, so I'll use that for my fixed limit of integration, and I will integrate to x of little g of t dt. it's just one particular indefinite integral. Right, so let's integrate this inequality. What I get on the left is minus epsilon over b minus a times x minus c when I integrate is less than capital G of x. Now, because I've dropped to a partial sum, I have only a finite number of terms, and so the rules of integration apply to finite sums. I can just integrate. They're all derivatives. And so when I integrate, I get the sum from 1 to n of fk of x minus fk of c. And then on the right, I get epsilon x minus c over d minus a. Now, because c is somewhere in the interval, x minus c is bounded above by d minus a, and therefore the absolute value g of x minus the sum from 1 to n fk of x minus the sum, or plus the sum from 1 to n fk of c is at most epsilon, and that is for any x in AB. Now, since the sum from 1 to infinity, fn of c, converges, this is a finite number So that last inequality says that the series 1 to infinity fk of x is going to converge to capital G of x plus f. And I should specify at the moment this converges pointwise. But since g of x is the indefinite integral of a continuous function, capital G of x plus m is a differentiable function. Capital G of x plus m is differentiable with derivative little g of x, which is how we defined the sum of derivatives. since this is equal to the sum of the original functions, that means that original sum is differentiable, and we have just computed its derivative. So, therefore, the derivative of the sum 1 to infinity fk of x is equal to the sum of the individual derivatives. The one thing we haven't done yet is we haven't proved the uniform convergence of the original series. But we can do it from the inequality that's on the board. Since this series is converging to M, we've already chosen n large enough to make this true. If we make n even larger, this will be within epsilon of m. So, now choose n even larger. So that the sum from 1 to n of these constants, fk of c minus m, is less than epsilon. Then by the triangle inequality, I have the absolute value of g of x minus the sum from 1 to n fk of x plus m will be less than 2 epsilon for x in AB and n greater than or equal to some constant n1. But then this inequality says that these partial sums are converging uniformly to g of x plus m. Whether it's epsilon or 2 epsilon makes no difference. Therefore, the sum from 1 to infinity fk of x converges uniformly to capital G of x plus m on the interval AB. So that's the last fact. Okay, so what about that hypothesis? It has to be in there to avoid the following trivial example. We require convergence of sigma fn of c to avoid this example. Take all the functions fn of x to be the constant function 1. Certainly that series does not converge because it's 1 plus 1 plus 1 plus 1. On the other hand, when you differentiate the series, it's 0 plus 0 plus 0, which converges uniformly. So if you don't have the hypothesis that the original series converges at least one point, then you have no way of eliminating this example, where the conclusion is obviously false. sigma cosine nx over n cubed this converges uniformly on any interval AB because of the Weierstrass M-test. Those functions are all bounded by 1 over n cubed, and that's a summable series. Well, this is the result of differentiating term by term. The series, or rather, the differentiated series is sigma negative sine nx over n squared when I differentiate. And again, the Weierstrass M-test says that in infinity norm, these are bounded by 1 over n squared, and that's another convergent series. Which converges uniformly by the Weierstrass M-test. So the original series, well, it converges uniformly. In particular, it converges at a single point. The differentiated series converges uniformly, and we can conclude from what we just did that the derivative of whatever function this represents, cosine nx over n cubed, you're allowed to differentiate term by term and that is true on any compact interval. Well, if it's true on any compact interval, for any given point, you can always choose a compact interval that contains that point. And therefore, what I've written there, that the derivative of the sum is the sum of the derivatives, is true over the whole real line. You have to do 2 steps here because the theorem that I proved is only working on 1 compact interval. But it's an arbitrary compact interval. So by varying the interval AB, we get that term by term differentiation is true everywhere. So I want to tell you how all of this applies to power series. sigma an x to the n be a power series, then the following things are true. The set of x's where the series converges has one of the following forms. It could be the point 0, it could be the whole real line, or it could be a symmetric interval about 0, which may or may not include one or both endpoints. So it can be of the form capital R to R, open interval R to R, half closed, minus sign, for some capital R that's finite and non-zero. So these are the only possibilities when you consider the set of all points where a series converges, and all of those possibilities can occur. And capital R is called the radius of convergence. So that's the first statement. The second statement is the series converges uniformly on any closed interval minus little r to little r when that is strictly less than the radius of convergence. And the third statement is, well, if you have a series, you could differentiate it term by term, or you could integrate it term by term. So the series sigma an x to the n the differentiated series n x to the n minus 1, and the integrated series all have the same radius of convergence. And the fourth statement is absolute value of x less than or equal to small r less than capital R, we have that the derivative of the series an x to the n is what you would get differentiating term by term. So it's exactly what you'd hope for.
On number 2, whenever it says any interval, does that mean both open and closed of any kind?
Yes, because this is the biggest such interval. If you look at the definition of uniform convergence, if you have it on a set, you automatically have it on any smaller set. Okay. I'm not going to prove this in the one remaining minute. So let me just point out, let me just list the examples that you can check for yourself. Okay, so sigma x to the n over n factorial converges on the whole real line. Sigma x to the n converges on an open interval, -1 to 1. Sigma x to the n over n converges on half open interval closed on the left. Sigma -1 to the n x to the n over n converges on the half open interval, but now closed on the right. What am I missing? I'm missing a closed interval. Sigma x to the n over n squared converges on the closed interval -1, 1. And the only example we don't have is A. And for that, sigma n factorial x to the n converges only at x equals 0. Of course, any power series, when you plug in x equals 0, you'll get convergence. But in this case, anyway, all of this is done by the ratio test. And to check the endpoints, you need the alternating series test in these two, but not. Here it's just convergence of sigma 1 over n squared. Anyway, I'll leave it to you to check these. But what it illustrates is that everything I said in part 1 can occur. So we'll prove this.